So for students in the back, can you hear me? Okay, great. There are several questions about homework before the class, but I didn't have time to answer. So raise your hand. Any question I can answer.
So for the first problem, when it's like I have an abacus, I have all the information out of it, like stresses and displacements. But for part one and basically the question, it says plot of the overlapped, underformed, or deformed geometry with stress contour.
Yes.
What exactly are you looking for there? Like, is that like a screenshot out of abacus, or are we making a plot?
No. You don't draw it by yourself. No. So in abacus, you submit a job and it runs successfully, and then you check the results, and then in the results, it will show, let's say, displacement. It has a picture. Yeah, deformed, undeformed, stress, deformed, undeformed. And you can also plot it as overlap, like deformed and undeformed, and screenshot that one. And yeah, screenshot, yes. You don't draw it by yourself. Yeah. Any other question? Oh, remove the center node. Yeah, so remove the center node. You need to watch the tutorial 2. The whole second tutorial is about how to modify input file. So when you create that shape with the cross part, it automatically, by default, abacus will automatically generate center node. And it also, when you run the job, when you run successfully, of course, it will generate input file with the center node in the input file. So what you need to do is that, let's say, first you have node definition, you have the element definition. So let's start from the node definition. Node 1, coordinate, x coordinate, y coordinate. Node 2, x coordinate, y coordinate. Let's say, I think in my tutorial, in the example, I use a this is what I did in the tutorial, right? So basically, we had 1, 2, 3, 4, 5. And the input file generated from abacus, after you draw this sketch, this one in abacus, it has the definition. Node 1, x coordinate, y coordinate, node 2, x coordinate, and node 5, x coordinate, all 5 of them, right? So in that definition, you need to remove this node. So basically, you keep 1, 2, 3, 4. And this is node definition. And for the element definition, the definition of the element is the element label and the first node, the second node. But of course, it doesn't matter for the one, like first or second. So let's say this is element. Let's use different color. Element 1, 2, 3. Original element, let's say 4, 5, 6. Right? But what you need to do, so probably you will see, well, of course, when you sketch a different way, abacus will generate different node label. But let's say if we assume we have something like this. So for the element definition in abacus input file, the definition for element 4 will be 1, 5. And for element 5 will be 2, 5. Element 6 will be 5, 4. Or element 7 will be 5, 3. Right? That's automatically generated from the abacus. But what we need to do, since we need to remove this node and also remove 2 elements, and of course you can also remove 4 and 5, keep 6 and 7, it's same thing. So what we need to do is that in the element definition, you need to define element 4, 1, 3. Now it becomes single element connected with these 2 nodes, and element 5, 2, 4. Now this become the one element, this become the one element, and there's no center node in between. And there's a great question before the class, like, is there a difference? Like, there's a center node, there's no difference, no center node. Yes, it will make difference because you can just consider if the center node is more function as a pin joint. And if I have a compression, I mean, if it is a single element, you have compression, you're fine, as long as it does not collapse, right? Your stress lower than the strength of the material is fine. But if there's a center node here, and you apply a compressive force, it will collapse. So it does make a difference with center node and without center node. And what I talk about is in the input file, how to modify the input file for the node definition and element definition. Yeah, and of course, in the node set and element set definition, you also need to change. Let's say originally they probably have they put the element set from all these 7, put one set, or let's say if the cross section has higher the diagonal has different cross section, then you probably put this one in one group. I don't know, some students did that as student office hours. So you need to check the problem statement. But let's assume that if this one have same cross section, and then the diagonal term has same cross section, so you probably need to put the element set. Let's say element set 1, element 2, element 3. Element set 2, you have 4, 5, 6, 7 original input file, right? And then in the graphic interface, you probably define, let's say, cross section this one, and you have the cross section definition for element set 1. And cross section for these 2, you have the cross section definition for element set 2. And now, since we remove these 2, so you need to change also the element set definition. So basically now, again, this becomes one set, and this becomes one set, and you don't have 6 and 7. And the same thing for node set, but node set that's probably for this one does not affect much, because let's say the original input file generated from Abacus, probably they put these 2 in one node set, and I say, okay, I apply force. So I have the F1 1000. It basically 1 means in the x direction, 1000 means magnitude, right? So it means that these 2 nodes are put in the same set, node set 1, and force applied here. And then I define node set 2. I put these 2 in one set, and I say, okay, constrain the displacement in the x and y. So in Abacus, input file, it says put this as node set and say boundary condition constraint 1 and 2. 1 means displacing in x direction, 2 means displacing in y direction. So for this simple case, it does not change much. But if you have more complicated situation, and now let's say you can change in any way you want. That if you have and then you probably need to put these 2 as force applied and these 2 as boundary condition. So yeah.
I wanted to know, when you putting which nodes your element is at, is there a pattern to follow?
You can define it any way you want. Any way you want.
Because port 5, element 5, you mentioned is from 2 to 4. But based on the example.
Oh, if the problem statement has already the defined node and element label, you need to follow that one. Yeah. So of course I can change this one to let's say you can start from here. 1, 2, 3, 4, 5, 6, 7, 8 original. So I don't really remember the details. The problem statement does require you have to follow the problem statement. Okay, so in this one you need to follow that one. So it's more require you to practice how to define the element and the node based the problem statement. Yes, but when you let's say have to graduate, when you actually solving the real life problem, it really doesn't matter. Again, your structure will fail or not, does not depend on how you define what is the number for each node, right? You can really put this as 100, 120, doesn't really matter.
So basically for my element 7, I could put either 1, 5 or 5, 1. Doesn't matter.
Doesn't matter.
Oh.
Yeah, doesn't matter.
Which type of stress we report with elements? Like we don't report the one by stress as a specific object specified.
What did the problem statement ask? S11? Element stress. So this is trust problem. This is trust problem, right? S11 means X. So S11 means sigma XX. So it's the actual stress. Yes. But of course, that's a great question because you can also say it's von Mises stress because in this trial situation, sigma XX equal to von Mises stress, right? Because let's say you have a state stress matrix, sigma XX, sigma YY, sigma ZZ, and this is sigma XX, YY, ZZ equal to 0. And you don't have any shear stress. So in the end, your principal stress becomes sigma XX 0, 0, 3 principal stress. And if you calculate the von Mises stress, sigma von Mises stress equal to, do you remember the equation, have sigma 1 minus sigma 2 square, square and sigma 2, 3, 3 minus 1 square. Yeah, it's, in the end, you get this one. So von Mises stress equal to sigma X, and which is the S11 in abacus.
For forces applying the node.
Yes.
Since we're changing the nodes, for yeah, changing the nodes, how it will know like this is the specific node that has the applied force.
I don't know what I mean.
So basically, let's say here was node 4,
Okay.
5.
Okay.
Now they're changing the nodes
Yeah.
to 4, knowing that.
So let's say, in the problem statement, this node is node 4. This node is node 5, right? So, for this problem, you need to follow my definition of node label. So what you need to do is that, okay, you define, let's say, what is the x coordinate, y coordinate. So you have node 4, x coordinate, y coordinate, node 5, x coordinate, y coordinate. And then in the node set definition, you put this one node as, let's say, node set 1, and you put 4 and 5 in it. And then in the force applied, you will have node set 1 and force applied in x direction, which you put 1 there. And then what is the magnitude of force applied? It's say 1000, you put 1000. Yes, this is how we apply the force at these two nodes. And similarly, let's say if this is a boundary condition and you have definition, okay, what's the coordinate? Node 6, x coordinate, y coordinate, node 1, x coordinate, y coordinate, and you put in one set, let's say this is node set 2. And in node set 2, and when we put in boundary condition, I said, okay, node set 2, 1, 2 means you cannot move in x direction, cannot move in the y direction. Makes sense or not? Okay. Any other question? Yes.
Says to bending moment and shear force at node 3 using 2 different methods.
Yes.
What would be one of those methods? What we've done in class. What would like a second method be?
We done in class. Let me show you. I showed both methods in class. So I don't expect you guys to create any method by your own. See, this is second method. Let me repeat again. So first method is based on the sign convention. Thank you. Since we know the K times Q equal to F, right? And based on sign convention, so this is sign convention of the internal force, which means shear force bending moment. This is a sign convention. This is a sign convention for external applied force, always follow coordinates, as long as we put this as x coordinates, this as y coordinates. So, and of course, magnitudes are all the same. So based on the difference in sign convention, we know that at the second node, positive, 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 positive. So they are the same, right? That's why F2, shear force at node 2, C2, bending moment at node 2, that should be the same. But the first node, based on sign convention, downward is positive for internal force, upward, again, based on coordinates, is positive. And for the internal force, clockwise is positive at the first node, counterclockwise is positive as first node. So now that's why, even though they're same magnitude, but you need to add negative sign, simply because sign convention. So this is the first method of calculating bending moment shear force at a node. And I think the question asked about the bending moment shear force at node 3.
Yeah.
Yes. So yeah. So basically now you have a system with 2 elements. Node 3 is basically the second node of element 2. Makes sense or not? Second node of element 2. So this is the first method. Second method, we have the function of deflection displacement in the y direction as a function of s. So based on definition, bending moment is second derivative of the deflection times EI, of course. So this is our second derivative of shape function because v and theta, they're constant. So this is the one you can use directly for bending moment. So basically here, you just plug in any s value, you can get the bending moment anywhere within the beam. And similarly, take one more derivative, and because the sign convention doesn't have sign in front, you can calculate shear force. Yeah, this is two methods.
This value, since there's two elements.
What do you think? The question asked about node 3. Yes. S is only for that specific element, always 0 to 1. So if I have a system, where is it? I cannot find it. If I have a system with two elements, I don't know what the boundary can, let's just assume, doesn't matter. This is element 1, node 2, and element 2, node 3. The question asked about bending moment shear force at node 3, right? So basically, it's the second element, and node 3 is s equal to 1. Yeah.
This is the example 1 for the sign convention.
Yeah.
In the K matrix.
Yeah.
Things like you also consider V1 and data 1 in your degrees of freedom. Like
Yeah.
here, I didn't get why this part is included.
So what's the question?
Like since we only have V2 and data 2.
Yeah.
Um,
Yes, you can skip these 4 components. Yes, you're correct. Yes, it doesn't matter because if you multiply by 0 is 0. Oh, you don't need those components. Any other question? So you guys are okay with homework? So it's due tonight. So I'm not saying it would happen tonight for any of you, but based on my past experience, it's like anytime when there is advocacy involved, we always have students have computer crash right before the deadline, have Wi-Fi disconnected right before deadline, have your pet distract you from submitting the homework before deadline. So just make sure that be prepared. Maybe submit 7 minutes earlier. Don't wait till like 11:59, and then you have problem submitting it. And also, I will have office hour from 2 to 4 today, so you can always stop by. It's really hard for me to like answer a question through email, so I highly encourage you guys to come to my office hour. So let's continue our topic last class. We talk about the stress, strain. Based on definition, normal strain in the x direction for 2D plane stress problem is du partial derivative of the displacement in x direction with respect to x. And similarly, normal strain in the y direction, v and y, and shear stress, uy vx. This is definition from mechanics materials. And based on what we derived for the u, we have n1 u1, n2 u2, n3 u3. For the v, we have n1 v1, n2 v2, n3 v3. So we have all this derived. Strain, and we put into the, why still here? I thought I erased it. So this is the conceptual part, and of course we put everything into the matrix form. This is the exact same thing as combining these 3 equations. And let's try to solve an example problem. This one. calculate the strain and stress in this element. So it's the same example in the last class where I asked about calculate displacement at 5 and 10 and calculate displacement at 4 and 4. We talked about two different methods. Well, actually, it's a standard method for calculating the displacement at any point, and also if the point on the edge, we have a simplified method. So, but those are all about the displacement. Now, it's the same problem here. Calculate stress and strain, strain and stress. Of course, you calculate strain first and then calculate stress. How should we do it? We already have. You have a question? No. We already have all the B and C, right? So basically, it's really straightforward application. We already have all the B and C. We already have all the U and V. We just plug in, and we can get a strain, right? So I will write here. It's the same example we did in the previous class. Just add one more question. So strain in the X direction based on our equation B1, U1, B2, U2, B3, U3. Now let's check. Well, actually, let me move this part here. This is our U and V. So now we can see that U1 equal to 0, U2 equal to 2, U3 equal to 0. So we only have one term. We also calculated in the last class 1 over 2a, 200, B2 equal to 20, U2 equal to 2. So this is 0.2. Similarly, strain in the y direction equal to C1, V1, C2, V2, C3, V3. We have V1 equal to 0, V2 equal to 0. So again, we have one term left. So 1 over 2a, 1 over 200, C3 equal to V3 equal to 1. Why is this one here? Shear strain. Gamma xy. 1 over 2a, C1, U1, C2, U2, C3, U3, plus B1, V1, B2, V2, B3, V3. U1 equal to 0, U3 equal to 0, V1 equal to 0, V2 equal to 0. We have two terms. There's a coefficient also equal to B2 and a C3. B2, C3. Oh, C2, B3. This is 0, negative 10. So actually, we only have one term because C2 is also 0. So 1 over 200. B3 equal to negative 10, V3 equal to 1. So So this is the normal strain in X, normal strain in Y, and shear strain. Any question? It's really just use the equation we derived and then plug in. And of course, for this example problem, since in the previous step, we already have expression of the U and V. So actually, it might be easier we just use the definition of the normal strain and shear strain, because let's say we know partial derivative U with the X equal to strain in the X direction, so you just take the derivative of this one. And also you have partial derivative of V with respect to Y, you get a shear stress in the Y direction, right? So for this one, since we already have this one, these two expressions derived, it actually might be easier or save you some time during the exam. Just use a definition of the shear of the strains. So let's say, or you can use normal strain in the X direction, partial derivative of U with respect to X equal to 0.2. And normal strain in the Y direction, partial derivative of V, Y, shear strain, du, dy, dv, dx. But of course, this is based on if you had the expression of U and V ready in the previous steps. I think this might be easier. Any question? So next question, how to calculate stress? We have all the strain components. How to calculate stress in this triangle element, in the plane stress situation. Mechanics materials problem is not an FAA problem. It does not really, anyone remember for plane stress? This is, it's getting close, but this is 2D problem. I can remind you, this is 2D problem. We don't have force here. And also force of area is only for tension compression. Don't use force everywhere. And we don't have force here. Anyone remember? If we have all the strain components for 2D plane stress situation, how to calculate stress?
I feel like you calculated the stress in X and stress in Y. Calculate the image like your
Calculate stress in X and stress in Y.
elementary column movement.
Yeah, that's my question. So how to calculate stress in X and stress in Y? Yes. So let me remind you guys. The first answer was Young's modulus. Yes. Young's modulus, when you say stress equal to Young's modulus times strain, that is only applied to 1D tension compression. Only applies to 1D tension compression. You have stress equal to Young's modulus times strain. Once you become 2D, remember your mechanics materials professor may demonstrate something like you have a film. Most professors have the film, and when you stretch it, it's not just elongation on the x direction, you also have contraction in the lateral direction, right? So the ratio of elongation and contraction becomes Poisson ratio. So for 2D problem, it's not just Young's modulus. It's not simply sigma equal to Young's modulus times strain. It also involves contraction on the lateral side. So there's a matrix, C matrix. You don't need to memorize C matrix, but you need to understand that it involves both Young's modulus and Poisson ratio. Question?
Is this like Cook's law? This looks like Cook's law, or it's like
yes, similar, but for 2D situation. Yeah, 2D situation. So again, I will write this equation here directly. I do not expect you guys anyway you to memorize this one. I will provide in the exam. Stress in X, stress in Y, shear stress, tau xy, Young's modulus, 1/, Poisson ratio, 0, Poisson ratio, 1, 0, 0, 0. And this vector, of course, the 3 strain component. Looks familiar? Yeah. Let's add, so since I forgot to give the Young's modulus Poisson ratio in the problem statement, let's just add some random number. It doesn't really matter. I just want to show you the calculation process. Poisson ratio normally 0.3, and let's say we have Young's modulus 70 gigapascal. Let's try to calculate the stress here. We convert everything to Newton and meter, so it becomes Pascal. Strain in the x direction, strain in the y direction, and a shear strain. And I will give you the final answer directly. Gigapascal, and to make it less confused, I still put it as Pascal, 10 to 9th Pascal. So this is a stress, how we get stress from strain for 2D situation, for plane stress situation. But of course, for plane strain situation, the symmetry is different. But I don't plan to talk about in the class today because majority of the real life problem for 2D problem is the plane stress. But just realize that the symmetry for plane stress and plane strain is not the same. Any question here? 9. Any other question? So again, some feedback and suggestion from exam 1. Some students said I need to show like how really the algebra of how to calculate the things in detail in class. Basically, let's say for example how to multiply this one, and get this one. I wish I could do that if we had infinite amount of class time. But because I mean, you guys always want as detailed as possible. I show all the calculation part to you, but department want to push me to cover as much content as possible. So I need to find a sweet spot, like how to make it reasonable. Unfortunately, I cannot really show the calculation part, and the really calculation part is not the key thing of FEA. It's something you learn before FEA. And also, I want to say that in our exam, we don't really like penalize your calculation really that heavily. If let's say if you have everything here correctly and you have mistake in this one, we only give you 1 point penalty. So and for specifically how you calculate this one to get this one, check your lecture notes. In the first 2 classes, I did a review of the matrix vector operation, but I cannot repeat like in every class. So how department evaluate my performance is basically how much content I can cover, and also if I'm the one who caused a grade inflation. That's the department really hate. It's if like a professor give everybody A, that's a big huge problem. Students may like it, but it causes a lot of problem to me. So I just want to say that I don't have infinite amount of time. And also some students suggest that I skip a lot of steps and they specifically say that if something multiplied by 0, it's better to write it out. Let's say what is C1 times 0, C2 times 0, 0 times U2. Again, we don't have that much amount of time to rewrite something times 0, something 0 times something. And also I want to say that as engineer, my recommendation that you don't write that one. You don't spend your time on those things. I know some of it's like really perfectionist, but as engineer, you need to know that as you goes more and more advanced, you can go to your project and everything. If you want to really go to perfection in every detail, you will not get the final results. Because so one thing that I'm doing the collaboration with the College of Dentistry, the professor in orthodontist this semester. They want to do some stress analysis. Let's say you apply force on the teeth, and they want to figure out the maximum stress on jawbone. Because a lot of times, if the force is applied too large, it can cause too much stress on jawbone, and it will cause the pain here. So they want to do some stress analysis. And my whole work last night, I work until 2 a.m., is to simplify the model to round like all the sharp edges and all the details. Because we know that when you apply the force on the teeth, and you know that based on your understanding of, let's say, your cast materials, you know, if you get this shape of the bone and you have force applied here, actually, you know that maximum stress is around here, right? You know that maximum stress is around here. So the rest, if they have small holes and small sharp edges and all the details, it really doesn't matter. You don't want to go perfection like, oh, I want to keep all the detail of the jawbone, all the detail of the tooth and everything. If you really want to to be perfection in all the models, they basically scan the patient and have the model, and you cannot really import into the abacus or ANSYS. And I'm not saying that it's student license. Student license, you can only use up to 1,000. I'm using the research license. It's much more advanced than what you guys use. But even with the research license, if you want really like perfection in every detail, the model itself cannot be imported into the FEA software. So my job is how to make it smooth, remove the details. So my work last night is like, originally when I put it in there's a geomagic, especially for medical FEA. The original patches, you guys probably use SolidWorks that like patches if they scanned the real model, is 800,000, and I reduced it to 20,000. So that's my whole work last night. So I really want to say that as engineer, your job is not really go to perfection in every details. If you really want to like keep all the details, like the small holes and the small point everywhere, you will not get final results. You will not. So in this project, you know that as long as I keep the shape here, the maximum stress, I know the maximum stress around this location, I keep the shape here, keep it as close as possible for the rest part, it really doesn't matter, right? So that's and also of course FEA is not just for mechanical engineering or aerospace engineering. If you learn, if you have a solid understanding of FEA, it can be applied to a very wide application, like in the medical. Yeah. So let's move on to a new topic. We talk about interpolation, we talk about how to calculate strain, we talk about how to calculate stress, and all of these are based on we know the nodal degree freedom, right? So now our question is how to calculate nodal degree freedom. Back to K, Q equal to F. We know the K, we know the F, we can calculate Q. So let's first try to figure out how to find a stiffness matrix for CST element. It's in chapter 6, section 3.3. for constant strain triangular element. If you remember in the bin element, we did something very similar. So for the bin element, when we derive the K matrix for bin, I talked about, okay, we have the deflection function based on the shape function, and it's N1, V1, N2, theta 1, and N3, V2, and N4, theta 2. And then you can have dv dx second derivative and integrate, that it becomes a strain energy density, and integrate becomes strain energy of the entire bin. And if in the end you can write that expression as half of q times something times q, which is in the scalar product operation is similar as half of kx squared, right? If you can write a strain energy in that form, whatever you have in the left, like something half of k q times coefficient times the q, then that coefficient becomes the K matrix. So here we are doing the same thing. Let's find the strain energy of the CST element, and we separate the Q out, and whatever left in between becomes a K. So the big procedure is the same as what we did before. So for strain energy, strain and density is strain times stress, but of course, since everything is in vector, so we need to use transpose of the strain vector. dV. And I think I forgot to put this one as, let's add here. We normally define this one as this matrix as B matrix. So this one simply becomes a strain vector equal to B matrix times degree freedom Q. Right, so this is strain. And stress equal to C times strain. So this equation, strain times stress, we can write it as, again, half integration of the volume means integration of the CST element. We have the Q transpose B transpose C B Q dV. So let's still repeat the equation here. Strain vector equal to B matrix times Q, no, the bigger freedom vector. So basically, this is a strain. Strain times C matrix equal to stress. Again, this transpose is because it's matrix vector operation, you need to satisfy the size need to match. So this is also strain. Now, these 5 terms here, multiplication becomes strain times stress. Volume. Yeah. So here I want to say that yes, it's we simplify as plane stress, but to know that the simplification is based on the stress in the let's say this is plate. The stress in this direction is much higher than the stress in this direction, the thickness direction, right? That's why we simplify as a 2D plane stress situation. It's a stress is much lower. But normally we would still consider this one has a thickness. So for this integration of volume, basically this 3-dimension multiplication, and you consider the thickness is not really 0. Yeah. Any other question? Yeah, so let's make it a little bit clear. So let's put different color here. This is stress, and these three terms become stress. I think this might be easier for you to understand. This is strain, this is stress. Strain transpose, Q transpose, B transpose. So this is corresponding to this part, and this is corresponding to this part, right? Thank you. Yes. Now let's check this integration. Again, let's say for the volume, it has this plane has x direction and y direction and z direction and everything. And if any of these terms is a function of x and y and z, then we need to keep into the integral. If these terms are the constant, then it doesn't matter. Then it basically becomes the multiplication of these 5 terms times volume, right? So again, back to our constant strain triangle. It's time. 2 minutes. Based on our definition, our derivation here, of course, Q degree of freedom is constant. B matrix here, we talk about constant strain triangulated, it means strain constant. Here, B matrix is constant because you can see these all B's and C's is calculated based on the XY, X1, Y1, X2, Y2, X3, Y3. There's no variable X or Y here. C matrix is pure dependent on the material property. You use aluminum, you use steel, the Young's modulus will be different, Poisson ratio will be different. This is also a constant term. So now let's check these 5 terms here. Constant, 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 constant. So the integral is simply equal to multiplication of these 5 terms times volume of your element. Make sense or not? There's nothing you need to do the integration calculation. I will continue in the next class. Thank you for coming and have a great day.